So our last session is going to be presented by Priyank Jain on behalf of Stafford U. So Priyank is leading our product management for Calibre interfaces here at Siemens EDA. He brings over a decade of experience in the semiconductor design and manufacturing industry, having previously worked and led product marketing and applications teams for KLA for EUV mask inspection and wafer metrology systems. He received his master's degree in system control and automation from the prestigious Indian Institute of Technology. And he will be presenting on behalf of Stafford U. Stafford U is a specialist in SoC physical verification, taped out numerous designs since 1998, from his early days at ATI transitioning into AMD. His experience with several foundries, including TSMC, Global Foundries, Samsung, UMC, and worked with multiple process nodes from 0.35 micron to latest process nodes. He definitely understands the pain points of the physical verification methodology. And he has been mentoring team members as well to become more technically independent. He's also worked closely with Siemens R&D on rule deck development and Calibre debug and optimizations. So with that, I'll hand it over to Priyank here. Thank you.
Cool. Thank you, guys. I should have brought my jacket. This room is very, very cold. Yeah. Okay, so first of all, I want to start by thanking Mr. Stafford U, I think, and his team, Go, Ken Lo, and Anthony Chow, and the entire AMD evaluations team. It has been a great collaboration with this team here, and we got a lot of learning, got a lot of feedback. So I want to just start with the thank you note here. Okay, so here's the agenda. You guys can hear me, right? Awesome. So here's the agenda. So we'll start with challenges contributing to long iterations, particularly the challenges AMD team was facing, the evaluation overview, and with these challenges, we got into the evaluation of the product called Calibre Vision AI. So we'll go into the evaluation overview, then a quick introduction of the product, the evaluation highlights, recommended enhancements from the AMD team, and I'll close with key insights. Okay, challenges. So long gone the days where things were serial, right? We'll wait for the blocks to get cleaner and then start the chip integration. Today, the chip integration starts much early, right? Engineers don't wait for the blocks to get cleaner, DRC and LVS clean, right? Essentially, as the block designers and block engineers working on building these blocks, the chip integration also starts much early in the process. We call it our RTL.3, RTL.5. You might have heard these phrases, right? And what happens when the chip integration starts much early, you get millions and billions of errors, sometimes trillions of errors, right? And because you get billions errors, there's one big challenge, which is your result database, which is coming out of your DRC run, gets massive, right? It's hundreds of gigabytes. And working around that big database is very tedious, it's time consuming, and all the challenges that I'm going to list kind of revolves around that. So what are the challenges that AMD team was facing? First of all, very large ASCII results database. We talked about that in the previous slide, and some files were 50 gigabytes that AMD team was facing, and highlighting let's say 1 million errors for a particular check onto your PNR tool or onto a design viewer. It's very slow. The rendering is slow, the highlighting is slow, the whole process becomes very tedious, right? So large results databases were posing a lot of challenges here. Then to handle these large results, right, what AMD was doing was limiting the results per count. So instead of running all results for all checks, they were saying, okay, I'm going to just do 1,000 results or 5,000 results for these checks. And what that would do is, if you limit the counts per results, if you're limiting the checks, it's very difficult, sometimes gets challenging to identify the systematic issue that's happening across the chip. What might happen that the 1,000 results you limited might be coming from a specific cell or specific block, and that prevents you from identifying what's happening at the chip level. And that because of that, it takes multiple iterations. And it prevents engineers seeing what's happening at the full extent. Then once let's say if you're limiting the results, but there are thousands and thousands of checks, like 1,000, 2,000 checks, and you get, let's say, 10 million results. Navigating and finding patterns, finding systematic issues with those thousands of millions of results, you need an Einstein, right? You have these experienced SOC engineers who have been working in these companies for 20, 30 years. For them, it gets easier to identify or recognize the patterns, recognize the groups. But then you have these relatively new users who are joining the semiconductor force. And it's challenging for those inexperienced users to understand what are the complex combinations of various checks. And it's going to take time for those guys to become Einsteins, right? And last but not the least, so all of these challenges were contributing to the long cycle time for full chip DRC analysis. For a dirty design, it would take about 2 to 3 weeks between DRC iterations. And then many of these factors were contributing to that delay. So the goal for AMD was to reduce this long cycle time. And let's get into the evaluation criteria. As I was saying, the goal was to find a solution that would target that chip level integration and DRC analysis, especially at the early and dirty stages of the design. The design that AMD used in this evaluation was a custom APU at 3 nanometer technology. And then there were multiple teams involved in the evaluation. So we collected feedback and findings from various teams at AMD. Okay, with that, let's get into the introduction of the product and evaluation highlights. This is the product, Calibre Vision AI. So it's a high capacity and multi-threaded engine. It loads super fast. And I'm going to talk about some loading performance here. But the result loading and navigating around billions of errors is very, very fast in Vision AI tool. And it has its own inbuilt layout viewer, which gives the ability to view the design sandwiched with heat map and results. So you can see a sandwiched view. You can analyze which blocks are dirty, right? So you see these red areas, okay, these are the areas where I have highest density of my violations. So I need to dive into these areas. And then all the panels, check panel, cell panel, layers, all of these are dynamically synced together. These are dynamic panels. So if you're looking at specific area of a design, all your panels will sync with that. And then this tool uses AI to analyze these billions of errors and create clusters based on the similarity, based on the root cause. So for example, if I have these 5 million violations that have common root cause, this tool is going to group all of these violations and create a thing called signal. We call them signal, meaning clusters. Now, this tool is production released in 2025.2, and Siemens is launching it at DAC this year. Okay, now this is specific to AMD. So this is one of the data sets that the team was using. And essentially, Calibre Vision AI uses Oasis. It doesn't use ASCII, right? So since it uses Oasis, and there is a lot of compression techniques built into Oasis files, right? We can compress the size to a much higher degree. And what that would yield is, that would yield into a much smaller result database compared to ASCII flow, which would load into Vision AI because Vision AI is multi-threaded. So it's loading super fast. The file size is smaller, and highlighting becomes really fast. And on top of it, you're not limiting results. You're not limiting results per check. With this tool, we are generating, or customers are generating, all results for all checks. And even with that, the size of the Oasis file is much less compared to ASCII. And then these files have all error markers, and with the across the view heat map, customers are able to visualize what's happening across the die. And in the bottom, we have a couple of examples here that shows signals grouping or AI-based clusters. So I've highlighted two of them. So you see signal 17 here, which is S13 and L1 group. It has 11 checks grouped together with 1.6 million flats. So meaning for customers to review these checks one by one or trying to find which checks go together, this tool is grouping these 11 checks because all of these violations are associated with a common root cause. And the idea is you look at these signals, you look at these groups, right? You understand which one should I look first, you prioritize, you find that root cause, and with a same set of fixes, you handle millions and billions of violations together. So that's the idea. In this case, for AMD, there were total more than 600 million violations coming from 3,400 checks. And what Vision AI did, it analyzed all these together in minutes and created 381 signature groups. So instead of reviewing these checks one by one, customers would just look at these signature groups and find patterns. And because of that, the turnaround and getting to the cleaner full chip is much faster. Here I have another example, which is signal 12, and I have the second slide kind of gets into the detail of what this signal is. It has 8 checks grouped together and total 2 million errors. Okay, let's dive into that. So signal 12, as I was saying, 8 checks grouped together and close to 2 million violations, and this was the heat map. Now, with a quick view, you would notice that most of my violations are centered in this big blob, right? For IP reasons, we can't really reveal what's happening inside it, but for an experienced designer, they dived into this and they immediately knew, okay, this is happening with my block and this is how I need to fix it. And they would assign it to an owner and write user notes that use this script or use this methodology to fix these blob of errors. So that's the idea. I have another example of signals. So here, in this case, we are looking at the signal 13. Right, again, we have 15 checks grouped together and close to 2 million violations. And the check panels, when I select this signal, all the check panels dynamically synced and will tell me what are the checks associated with this set of signals. And as you can see, all of the checks are either M0, metal 0, or cut metal 0. Now, for an experienced designer, they would know what's happening with this guy, right? But for a relatively new user, what they can do is they can look at checks, they can look at the heat map, zoom into a few blocks where they have highest density of the violations, and they would immediately know what is the systematic issue here. Again, for IP reasons, we can't really zoom into these areas, but yeah, this is something that was very apparent when the designers zoomed into specific areas here. And the whole idea is, instead of reviewing thousands of checks, you look at hundreds of signals or hundreds of groups, right? And recognize that common failure pattern. And this was one of the examples. Okay. Now let's get into the recommended enhancements. So one of the feedback that we got from AMD was, yeah, this tool is good, but then it needs to have these A, B, C, and D, these 4 items to make it very useful for us and make it more cohesive with other solutions we have from Calibre. And one of them was incremental DRC output, right? So as you guys know, full chip SoC runs or full chip DRC runs are longer sometimes. It could take 2 days, sometimes 3 days, right? And nobody wants to wait for the entire run to get finished and then start analyzing what's happening inside the design. So one of the feedback we got from AMD was to implement the incremental DRC output where you don't have to wait for the run to finish. You can start analyzing as the checks are being completed. So you're incrementally loading the results onto the tool Vision AI. Very, very important and interesting feature that currently we're working on. The second one we got was ability to filter results globally and ignore results by check or sell. So for example, that the full chip owner has the entire DRC run. Now he might be interested only at the interfaces of the chip, right? He might not be interested inside what's happening within a block. So what designers would want to do is they would want to weigh or filter out the results inside the block or at certain areas of the chips by either cell basis, check basis, block basis, and then look at what's remaining. There was another feedback that we got. Then two more. One of them was grouping by signature. So today we have this, the groups or the signals panels. This is the view that we get. One of the feedback from AMD was to have hierarchical view where have multiple signatures and you can analyze a group of signals based on signatures together. And last but not the least, integrating the waiver flow in Vision AI, where customers can review the violation, they can find the fix, and then waive those results and move on to the next set of results. So integrating waiver and generating waiver file from Vision AI, that's another interesting feedback we got from AMD. Now let's get into key insights. So what did AMD find after using the tool? Okay, so if I want you guys to take anything home from this talk, this is it. AMD is achieving 40 to 50% reduction between DRC runs with Calibre Vision AI. So 40 to 50%, meaning that they're spending 3 weeks between DRC iterations. So with this tool, they're able to cut it out from 3 weeks to 1.5 weeks. And these are more insights. So one of them is the tool is very high capacity. It loads results very fast. To overcome some of the database performance related issues they were facing with the ASCII database. Then with AI-based grouping, the tool identifies systematic issues much faster. That's occurring across the die compared to the existing solution. And then automatic signal and signature grouping focuses on grouped checks to quickly identify the root cause. So these are the checks that SoC designers would look and find into their existing solutions. And what Vision AI offers is this automatic signal and signature grouping. And with all these features combined, AMD was able to achieve 40 to 50% reduction, and they were able to meet their DRC debug turnaround time on a complicated design. And it would save them several days per iteration over their current methodology. And then based on the 4 features we heard recently, what AMD really believes that while building additional tool experience and the new functionality, they will be able to achieve 70 to 80% improvement in full chip DRC debug. 70 to 80% is 4 to 5x. So achieving a 4 to 5x improvement is going to be really, really huge for not just AMD, but all the customers. And that's all.